Hi everyone. Today I will walk you through a machine learning project where we predict the electrical power output of a combined cycle power plant. I will cover four key areas: how I choose my metric and algorithm, the feature analysis, the final model, and its evaluation. First, I choose RMSE as my evaluation metric. RMSE tells us the average prediction error in megawatt. So if our RMSE is 3, we are off by about 3 megawatts on average. I choose RMSE over MAE because RMSE penalizes large error more heavily, and in power plant context, a big prediction miss could affect grid stability, so we want to minimize those. For algorithm, I compared to linear regression as a simple baseline that assumes straight line correlation, and random forest which builds 100 decision trees and average them to capture more complex pattern. This chart shows the comparison visually. The blue bar are all four features. The orange bar uses only top two. The two key takeaways: first, random forest beats linear regression in every configuration. Second, using all four features is always better than just top two. The best the best combination is random forest with all four features at 3.46 RMSE, which is what we selected as our final model. Looking at the heat map on the right, we can see the correlation between all variables. The dark blue cells show strong negative correlation. Ambient temperature has a minus 0.95 correlation with power output. As temperature goes up, power output drops significantly. This makes physical sense because gas turbines are less efficient in hot weather. Exhaust vacuum is the second strongest at minus 87. The pressure and humidity have moderate and weak correlation respectively. I compared using all four features versus just top two, even though AT and uh, we dominate, keeping all four features consistently reduce error across both algorithms, so I kept them all. The random forest model tells us which features matter most. Ambient temperature accounts for over 90% of the model predictive power. This aligned perfectly with our correlation analysis. AT had the strongest correlation at minus 0.95. Even though AP and RH each contribute less than 2%, they still help reduce the overall error, which is why we kept all four features in the final model. So here is our final model. It is random forest with hundreds decision tree using all four features. The scatter plot on the right shows predictive versus actual power output. Each dot is a test data point. The closer the dots are to the red dashed line, the more accurate the prediction. As we can see, points are tightly clustered around the perfect prediction line across entire range from 420 to 496 megawatt, which tells us the model performs quite well. For our final evaluation, the random forest achieved a test RMSE of 3.24 megawatt. To put that in a context, the power output ranged from 420 to 496 megawatt. So our error is only about 4.3% of that range. And that is quite accurate for predicting the real world power output. To wrap up, we used RMSE for our metric and selected all four features based on correlation and importance analysis, compared linear regression and random forest, and our final random forest model predicts power output within about 3.2% megawatt, a 29% improvement over linear baseline. Thank you.